So welcome back, guys. Today we continue. Just I want to close this section 4.1 about fast Fourier transform. And last time I've shown you how, in fact, we can work out the idea that when you have a large n, as it is described in this slide 16, well, you can split it in two, and you can use the n over 2 to obtain the Fourier transform matrix of lower size, n over 2. Okay, and we can continue with the ideal or the most accurate or the most appropriate factorization. We can continue this way to get back to our Fn. Okay, so what we described last time is a way to get this F and Xn by splitting the C vector in two parts, an odd part and an even part. Okay, and the last slide of the presentation, there is a description of the fast Fourier transform step using MATLAB. Okay, so my first goal today is to show you how to do it with MATLAB. Okay, so let's go through the iterations first of this pseudo code. First of all, what we are going to do, we are going to compute a first vector. We can call it y1, which is in fact takes the application of the inverse fast Fourier transform by MATLAB. Okay, on what? On the even coefficient C. You'd like to, in fact, you're moving from C to F. Okay, and in fact here we are dividing, instead of dividing by n, basically we are multiplying by n over 2 instead of multiplying by n. Okay, because in fact here you're just taking half of C. Of course, we are assuming that n is even. The y double prime, or what we can call y2 in MATLAB, is applies the inverse fast Fourier transform on the odd part of C. Okay, in the book they start from 0 and 1. Well, it doesn't work with MATLAB in the current implementation. And multiplied by n minus 2. This is the index on where to stop. So in fact, what it says, this command says that you start from the second entry in C, which is even, of course, and you are moving by a step of 2, and you start at the nth entry in C. Okay, so this way you have covered n over 2 items in C. And this is saying that you start from the first entry of C, you're moving by a step of 2, and you stop at the n minus 1 or n minus 1, let's say, item in C. So this way, in fact, you cover n over 2 items. So these are the two first main steps. Then you are computing a vector which is called D. And here there was a mistake. In fact, they were taking the conjugate. In the current state of the implementation of the MATLAB, they don't. In fact, in the book there is a prime here, which is not correct. It doesn't work like that. If you do it like that, you're going to get, in fact, let's say a vector instead of having a row. So what is this? Okay, this is, in fact, you are distributing W, which is here, as we said, it's e to the power 2 pi I over n. Okay, you're distributing it on the entries of D, going from a power of 0, so W to the power 0 is going to give you 1, to the power of n over 2, okay, minus 1. So basically, for example, if you have n equals 10, n over 2 is 5, so 5 minus 1 is 4. So you'll have W to the power 0, W to the power 1, 2, 3, and 4, 5 items. Okay, then you are assembling, you're using the y prime and the y double prime, or what we can call also y1 and y2. We can call them, we can use them to assemble, and we can use them to get back the y here, or in fact the f we want to start. Okay, so I'll show you right now how to do it with MATLAB. So I will share with you my screen. Okay, so here, in fact, do you see my screen, guys? Yes?
Yes.
Okay.
Yes.
Okay, so here, for example, I've taken a large C, and I've taken C, which is just taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you see, managed to have, in fact, an increasing C, and that's just for curiosity. You can try anything else. Okay, so I wanted to see what happens, but still, it's a little bit large. So imagine you are targeting F10, in fact. Okay, so I'm just making sure that C is entered as it should be. Here, N, of course, is set to 10. Okay, and first of all, I'm computing CE, which is the C evens. So what it is doing, as it is mentioned in the pseudocode, it is taking what? Starting from the second entry with a step of 2, and it stops at the last entry. So it took 2, 4, 6, 8, and 10, as you can see. Okay. Now CO for the odd entries, I'm taking, of course, I'm starting from 1. I'll stop at the one before the last. So I'll start from 1. I'll take 1, 3, 5, 7, and 9. And you see that it works. Okay. Now, first of all, I'm going to compute this y prime. Here I called it y1, which applies the inverse fast Fourier transform to CE, to the even C's. Okay. Multiplied by n over 2, of course. So here you can see that I obtained y1. Got it? So what is it? You see now, it's not a row or a vector of size 10, but it is a vector of size 5. It's 1 by 5 factorial here. Got it? Because I've taken 5 component in CE, okay, and multiplied by, of course, by 5. So it's just y prime here. Okay. Now I'll do the same with CO, with the odd part, CO. So I'll get y2, which is, of course, 1 by 5 row, and this is the CO, the y2 I obtained. Okay, got it? Now here I'm computing W, which I said it's e to the power 2 pi I over n. Of course, n was predefined to be equal to 10, preset equal to 10. So immediately it gives me back what is W. And here in this step, I'm distributing this W on the entries of D. So I'm saying like take from 0 to n over 2 minus 1. And here I can see that T, here it's W to the power 0, which is 1. W to the power 1, you see I get back W. This is W squared, W to the power 3, and W to the power 4. So this is the D vector I need. Of course, I needed to compose and get, in fact, y equals to FC, capital FC, okay, directly. So this is, in fact, immediately what I can get if I write the following. So it has 2 parts, of course, y. It has 2 parts. First one is y1 plus d multiplied by y2, and y1 minus d multiplied by y2. So you get exactly the following y. So this is, in fact, a computation of y, which allows you to apply the inverse fast Fourier transform faster, because you separated the problem, you split the problem in 2. Okay. In fact, you can here verify. So now, since I already have C, I'm just saying, like, that's out of curiosity. If I'm checking that if I could have obtained the same thing if I just applied the inverse fast Fourier transform function to C directly. Okay, and you can see that I have exactly the same thing. In fact, I should have divided by n, I think, somewhere. Okay? I think this y should have been divided by n, by 10, as you can see. So I'm just in here. So it should have been divided by. Okay, guys? Is that okay? Any question? So, in fact, from a computation point of view, this goes much faster to split the problem in two. And of course, if you have a large n, in fact, you end up decreasing the size or the number or the complexity of the computation by a consistent amount. For example, it goes from 1 million complexity to 5,000. Okay, for large numbers, for example. Okay, so this is for, I'll stop sharing here. So this is for the first part regarding the computation of the with the inverse fast Fourier transform, but with using this while factorization. So let me stop sharing here. Okay. So now I'll move on to, so this is it for lecture 22 or 4.1. Any question before we continue, guys? Okay, so I'll stop the recording now and I will continue with the new recording for the next section.